No questions? All right, I'm going to change the schedule a little bit. We have the formal lab write-up due next week. So I'm going to have you do one more thing, like I was saying earlier. And what I'm going to have everybody do is try a recrystallization of their chromium complex. Yeah, I mean, it doesn't take very long. And so you'll continue with your qualitative analysis today, in addition to start a recrystallization. The recrystallization, what it involves is just dissolving. So take a bit of your product, I would say half of your crystals, and then try to dissolve it. And so the question I always get asked is, how much water should I dissolve it in? Well, how much water should you dissolve it in? Just enough, right?
Yeah.
Just enough water. You don't want too much water, otherwise it's hard to crystallize again. So you dissolve in what we call a minimum of water. That's how much. And then you can add a little bit of ethanol to get the crystallization. You don't want to fully crystallize it out. You want the crystals to slow grow. And so you can just seed a crystal, that is, get it maybe started and then let it grow over the weekend. Yeah.
Would you do the filtration and over the or would you do the filtration again today?
No, the filtration's not until later.
Okay, just check.
Yeah.
Yeah. And last thing, we saw the examples of the scientific papers.
I'm sorry?
In your office, scientific paper examples.
I have some, yeah. You want to look at them again?
Yes.
Yeah, that's okay. You're welcome to look at them, except yeah, can't make a copy of them.
When you say next week, we go on the weekend, you want to do on Thursday? Or?
No, it'll be due the following week. Yeah, I mean, if you do a recrystallization, the basic paper is going to stay the same. You're just going to add a little bit at the end. And so you should continue working on it. But it won't be due next week. It'll be due the following week, yeah. But next week we have a test on on Thursday. No, just 15. Because your basic guys have those. All right, any questions? The lab write-up? I'm sure everybody will say Thursday. Push it. If I said Monday or Tuesday, I think people are going to start to ask. So Thursday.
25th. Yeah, 25th.
All right, thank you. Thursday the 25th of February.
We're not waiting for the
Yeah, try to get started on it.
When are we doing the unknowns next Tuesday?
You're doing the unknowns as soon as you finish your knowns. So that varies. You know, some people will finish it pretty quick and start their unknown right away.
And will we be doing a lab report for the unknowns or just the unknowns?
You will be doing a lab report for both the knowns and the unknowns. The lab report is very simple, though. You know, yeah. Basically, you have to write an observation and equation for each step of each ion's analysis. It's very simple if you write them down, but you know, some people just don't write anything down. Then they'll have to figure out all the observations and equations on their own. All right, so what's the next ion after iron? Was it aluminum or chromium? So if we just go along and then follow the flow chart, you know, we start off with some unknown. Aqueous that contains aluminum ions. We add HCl. We expect aluminum and HCl to have what? Aluminum 3 plus and HCl to have no reaction. You know, Al3 plus plus H plus plus Cl minus. I could write it in net ionic form or in combined form. And then, you know, we take solution 1 plus ammonia, and we should get a PBT here. It's a very faint color, white or colorless. Very low density precipitate. So we know the equation for this. Ammonia is a precipitating agent. It's a metathesis reaction. And then what? What's the next step? Well, no, I just want the next step in the flow chart.
Check for base. Make sure it's base.
No, not the step. Just, you know, just tell me what's going on. Well, chemically.
Oh, thank you.
Nothing. I mean, the ammonium's in there. You know, you add a little bit of ammonium to make sure the pH doesn't get too high. The ammonium is actually, you know, when you add the ammonium, you're actually hurting yourself because you're not going to get as much precipitate. And the ammonium is just there. But the ammonium is a product here, so if you add product here, it's going to shift it back left. But why do we do that? This is why to some people I said, Dad, don't bother adding the ammonium. Don't bother. You know, sometimes pH is critical. Here, pH is critical. We don't want the pH to get too high. We don't want that litmus to get too blue, right? Other times, pH is no big deal. Like, did you measure the pH when you were trying to re-precipitate silver chloride?
No.
Did it say to measure the pH or use litmus to get it acidic? Did it say use litmus? Till just acidic? How did you get it to just acidic?
That was the one where we stopped one drop before the precipitation, or as the precipitation stops. That was the
So you add ammonia to dissolve the silver chloride?
yeah, actually.
Did it say to test with litmus? It says to test with litmus. Is that necessary? It's absolutely not necessary at all. It's a waste of time, basically, because what are you doing? This is the final step. You're just going to make it acidic. If it gets too acidic, no big deal, right? There's no consequence to that. And so that in that case, in the silver analysis, is a waste of time to test with litmus. You know, so here it's critical that we test with litmus because we don't want it to get too high.
What happened? There's two bases.
Magnesium and the other 2+ cations will precipitate out. That's what happens if it's too
That's
basic.
critical to not be two bases. Not too acidic.
If it's too acidic, you have nothing precipitating.
So that is the next step.
All right, in the next step, we're going to make it too basic. I already explained why we're going to make it too basic. Why it's okay now to add lots of hydroxide. Why? why is it okay now to add lots of hydroxide, but before we didn't want to get the pH too high?
Just for the next stuff, it's the real neutral.
Well, in this case, all the other ions shouldn't be here. You know, assuming we did the separation well, it's just the precipitate that we're adding the hydroxide to. We got a CCS here. Lewis acid base reaction. And then what did we do? We added some hydrogen peroxide. What happened there? Just look at the flow chart and see. Yeah, aluminum 3 plus is already maxed out. We aren't going to form aluminum 4 plus or aluminum 5 plus, are we? No. And so aluminum 3 plus has lost all its valence electrons. We'd have to start ionizing core electrons next. It's not going to happen. We could potentially oxidize hydroxide, but hydrogen peroxide is not enough to do that. Okay, what's the next step? Oh, we heat it?
To get rid of excess H2O2.
To get rid of excess H2O2. Alright, so we could call this step 4A solution. But I don't want to get rid of it yet. I need the hydrogen peroxide to do something, so I'm not going to get rid of it here with aluminum. I'm going to get rid of it later. Okay, 5. And it doesn't matter if hydrogen peroxide carries on to the next step here anyway. We'll take the solution 4 and then do what to it? Yeah, plus HCl. It's going to look like nothing's happened, but something's happened. It appears like nothing's happened. The reaction that's happened is this. We're going to destroy a complex. Converting the hydroxyls to waters. Actually, that's a hexa-aqua complex of aluminum. But we just write it aluminum 3 plus AQ. Uh-huh.
But why won't we get rid of the H2O2?
We don't want to get rid of it now because we need the H2O2 to do something. What do we need the H2O2 to do? What's the purpose? Oxidize what?
The aluminum?
No. No, we don't oxidize. Aluminum 3 plus, we don't oxidize. It's already lost all its valence electrons. How many valence electrons does aluminum have? 3. So if it's plus 3, it has no more valence electrons to lose. We aren't going to oxidize aluminum. Look at the flow chart. You don't even have to guess. You just look at the flow chart and you can see what becomes oxidized. What becomes oxidized? The flow chart tells you the reactants and products for each step. All I'm doing is I'm balancing the equation. And so we're going to wait until the hydrogen peroxide oxidizes, not the chromate, but oxidizes the maybe I need to spend more time on reactions.
Aluminum chloride.
Well, not with the hydrogen peroxide. We'll look at the hydrogen peroxide later. Okay, 6. We have this. The next step of this is we're going to precipitate it out. But how? What are we precipitating now? What are we going to add to the aluminum? Well, we added the hydrochloric acid. What comes after the hydrochloric acid? Are you guys have the flow chart?
Yeah.
Yeah, just tell me what's the next step in the flow chart. Not barium chloride. Aluminum?
Aluminum, and then
All right.
and then
Solution 5 plus aluminum and
ammonia.
ammonia. And so we're going to add ammonia. And the aluminum, how much aluminum do we add? Just a little bit. And then we get a red PPT. Aluminum is like a complexing agent. It'll complex the aluminum ions, but we don't need that much because aluminum has a very bright color once it complexes. And so what we're going to do is we're going to introduce aluminum as an impurity. You know? And so there's going to be a little bit of aluminum incorporated into the precipitate. And so we're going to take our aluminum 3 plus 3 ammonia plus 3 H2O liquid and a little bit of aluminum to incorporate as an impurity, a dyeing agent here. And then we'll get aluminum hydroxide. But this aluminum hydroxide is not pure. It's impure. And so, excuse me, I'll indicate it with a double dagger. This is red. Normally, aluminum hydroxide is white or colorless. This is going to be colored red. And so, with this red PBT, this is called the red lake because aluminum hydroxide forms a gelatinous precipitate. And so when you centrifuge it, it almost looks like a liquid layer, but it's actually a solid layer. It's like Jello. If you're familiar with Jello, this would be like red Jello or cherry flavored Jello at the bottom of a liquid phase here. And so when you centrifuge it, they call it the red lake. They call it the red lake because it almost looks like a red lake at the bottom of your test tube, you know, where the water above it would just be the air. But it's not actually a liquid, it's a solid, a gelatinous solid. So it's a red lake precipitate. A lot of people get confused because a lot of people only look for color. For example, they just look for blue. Oh, I got a blue, that means it's positive. No, you have to know, is it a blue solution you're looking for or blue precipitate? Sometimes you're looking for a blue precipitate and you get a blue solution. Is that positive? It isn't. And so a lot of people get false positives because they get blue solution thinking, oh, that's all I need. But really in the procedure it said you're going to get a blue precipitate. And so I get a lot of false positives for things like, even for iron, you know, a lot of people just get a blue solution. They think they're done because they don't realize it's supposed to be a precipitate. This is a precipitate. So some people get a red solution, they think they're done.
It's a Jello.
Okay, chromium's next. Chromium 3 plus pass.
Plus barium chloride.
So we'll take our unknown, aqueous, and then if our unknown contain chromium, what happens with HCl? Chromium. No. Nothing happens. This is the first step of the procedure. Okay, then we take our solution from 1 and then add ammonia and we get a precipitate. This is a gray-green. Chromium, do you know what color is chromium 3 plus in solution? Anybody know? Maybe I would think around gray-green or green or something like that. Maybe. plus 3 NH3, 3 H2O liquid. Hydroxides are colorless. Okay, what's the next step here? NaOH. We'll take precipitate from 2, add NaOH. What should happen? Nothing. Some people ask why, you know, why doesn't something happen? There are two ways to answer it. One way of answering it is, well, it just doesn't. Nothing happens, right? But, you know, other people want to know a little bit more. So, you know, if you could be a little bit more informative about why it doesn't happen, that would be good. Or at least provide some kind of information.
Does it have to do with the coordination number? Yeah, the coordination number.
No. Indirectly it does, but no, not directly. We wouldn't talk about coordination number at all in answering why. But it's related to coordination number for sure. Kelly?
Why would you add HCl to the chromium? I didn't see that in the procedure.
That's what we're going to find out. You know, that's the question you have to. The question you have to answer is, why do we add HCl? So, well, we aren't adding it here. You know what we're adding next? We're adding hydrogen peroxide, not HCl. And then we get a what? Yellow solution. Is that right? So we got to figure out what's going on here. And so we know that the yellow is from what species? Dichromate's orange. Chromate is yellow. This is an example of a redox reaction, a skeleton redox, because we know that chromium 3 hydroxide, this gray green precipitate, goes to a yellow solution, chromate. And then we also know that hydrogen peroxide was the other reactant. What does hydrogen peroxide go to? Well, probably water, but any gas form? You don't know. But that gas could be something else. We'll just leave it like this. Hydrogen peroxide goes to something. Because in skeleton redox, do I have to worry about hydrogen and oxygen? No, because they're going to balance in the end. And so what do I do next? We balance each individually, right? 1 chromium, 1 chromium. 3 oxygens, 4 oxygens. 3 plus 2 is 5 hydrogens, no hydrogens. There's a charge. Plus 5 minus 2, plus 3, and 0. And so the half reactions like this. And just make sure it's balanced. Right? 1 chromium, 1 chromium, 3, 5 hydrogens, 5 hydrogens. 4 oxygens, 4 oxygen. 0 charge on the left, minus 0 charge on the right. It is a balance. This one, you know, this one we have a choice. This one we could just copy out of our redox chart. Or we could figure it out. If we were to figure this out, you know, we're gonna get, it's gonna end up going to 2 waters plus 2H plus 2 electrons. Or just copy it. And then we'll just add them together, right? So I'm gonna multiply this one by 2. Multiply this one by 3. Add them up. And so the net redox reaction that's happening is we're taking the 2 chromium, 3 hydroxides. The water will cancel. I got 2 waters here, 6 waters here. Well, let's cancel out those 2. So I'm going to go 3 H2O2s. It's going to yield 2 chromates. 10 H pluses. And 4 waters. Actually, the H pluses I should have canceled too. Let's cancel them right now. 10 H pluses here, 6 H pluses here. That's going to give me 4 H pluses here. This would be my net redox reaction. Let's make sure it's balanced. Is it balanced?
I don't think the hydrogen peroxide has balance in the beginning. It's a half reaction. H2O2.
Oh, this is not balanced. You know, I just wrote it backwards, sorry. I need to do this.
H plus is going right.
Yes. H plus is gone this way. So it would be hydrogen peroxide is 2H plus 2 electrons yields 2H2O. That's the correct one. You know, my electrons wouldn't have canceled out properly either. Stop. Let's fix this. So fixing this, I still need to multiply this one by 3. And so I'm going to get 2 of these, and then the waters. 2 and 6 waters cancel, and then 3 hydrogen peroxide, and then 6 H pluses and 10 H pluses. Gives me 4 H pluses over there. That's it. Okay, so let's see if this is still balanced. 2 chromiums, 2 chromiums. 3 times 2 is 6 oxygens, plus 6 oxygens is 12 oxygens. So it's 8 and 4 is 12 oxygens. It's 6 hydrogens plus 6 hydrogens is 12 hydrogens. It's 4 plus 8 is 12 hydrogens. The charge on the left is 0. The charge on the right is minus 2 times 2 is minus 4 plus 4 is 0. And so this is balanced. So this should be my net redox reaction. You know, driving force for this, you know, although I didn't write the driving forces. We know the driving forces are present for all these, otherwise these reactions wouldn't occur. But just to get some practice here, this is going to be my reducing agent. Here's my oxidizing agent. Going backwards, what's my reducing agent? The reducing agent going backwards will be chromate. And the oxidizing agent? The hydrogen ions? It's both, but really, what is the oxidizer? The hydrogen's the oxidizer? The oxygen?
I think it's 2 of them together.
The hydroxide? The H plus? Yeah. It's H plus both on the left and on the right.
So didn't we just
Well,
say-
you know what? You're probably very confused because chromate is not our reducing agent. Chromate's got to be our oxidizing agent. Because chromate's going from +6 to +3. And so what is our reducing agent? Yeah, -2 to -1 is the oxygen in water. The water is, H plus is a spectator, but we need it. Right? And so this will be our reducing agent. It's the oxygen. That brings up another point, and the other point is this in basic solution or is this in acidic solution?
Basic.
This is in basic solution. If I have hydroxide present, which I do, I have excess hydroxide present, is H plus stable in excess hydroxide? No. And so this is what we call acidic, but we know it's not acidic. So I have to fix this equation to make it stable in basic solution. So how can I fix it?
Add equal amounts of hydroxide on both sides.
Yeah, and so I'm going to add 4 hydroxides here and 4 hydroxides here. And so basic solution is going to be 2 chromates plus 3 hydrogen peroxides plus 4 hydroxides. So that would be the left side. And then this is,
That'll be right.
okay, let's go to this side. 2 chromates plus
Mine is right.
4 hydroxides plus 4 H pluses gives us 4 waters. 4 waters plus 4 waters is altogether
8 water.
8 waters. 8 waters. So this would be the Redox equation in basic solution. And you can see that the H plus is indeed kind of a spectator. Is it?
What happened to sodium hydroxide?
What happened to sodium hydroxide?
Chromium.
You put chromate on the left.
You put chromium twice.
This, I don't know, it just disappeared from my mind. So that's what happened. It's chromium 3 hydroxide. Yeah, right. So that would be the reaction in the basic solution, which is what we have in basic solution, not acidic solution. Same reaction would happen in acidic solution, except rather than having OH minus, we have H plus. All right, what's next step? Next step is any excess hydrogen peroxide we need to destroy. Why? Why do we need to destroy any excess hydrogen peroxide? So let's go to step
It
5.
interferes with the test for magnesium.
It interferes with the test for magnesium?
Wait, no.
How come it interferes with the test for magnesium? Will it react with the magnesium ion itself? Will hydrogen peroxide react with Mg2 plus? No. I mean, Mg2 plus is already oxidized.
Wait,
So it's
oh,
max.
I think I know why.
Why?
It's because when chromium reacts with the hydroxide, no. The hydrogen peroxide to become chromate, and it is incorrectly reported as AlOH3.
Yeah, there's a different reason for destroying hydrogen peroxide. And what we have to look for is we have to look for, well, hydrogen peroxide is a very reactive what? It's very reactive. It's like number 3 or number 4 on what? It's number 3 or number 4, depending on what chart you look at. On what? It's a strong OA, right? It's near the top of the chart. The hydrogen peroxide is a strong OA. Therefore, if there's anything that's a decent reducer that we're going to use later on, hydrogen peroxide might destroy it, you know. And so is there something that is a decent reducer that we use later on that hydrogen peroxide might potentially destroy? Yeah, maybe chloride. It could oxidize chloride to chlorine. That's possible. Anything else? I'm sorry? Ammonia and ammonium. Ammonia and ammonium. Do you have a feeling of the redox properties for ammonia and ammonium? What would you call them? Like, for example, this is a test question I give almost every year in Chem 1A. Ammonium ion is electron poor. And sometimes I'll say this, is electron poor because it has a positive charge. So it's, you know, missing an electron, so it's electron poor. True or false? False, yeah. The answer is false. We would think of ammonium as being electron, not electron poor, but it's electron rich. Why? Why is ammonium electron rich?
That's all electron because of the type it fills it.
I haven't heard the answer I'm looking for yet.
That's oxidation state, electronegativity. Like you add 4.
No, I don't want to hear about electronegativity or valence shell because nitrate has a negative charge. I ask this question almost every year too. Nitrate is electron rich or electron poor? Well, it's got an extra electron, therefore it must be electron rich, correct? No, nitrate is electron poor, so I don't want to hear about electronegativity of nitrogen or any of that valence. You know, you're going on the wrong path. I want to hear
Oxidation.
I don't want to hear -3. I want to hear oxidation state. And -3, unfortunately, that's not the correct oxidation state. What is oxidation? Recalculate it, David. You should know. On nitrate, what's the oxidation state of nitrogen on nitrate? +5.
Oh.
What's the oxidation state on
Oh, I see.
ammonia? And ammonium?
-4.
No, -3. Ammonia?
Sorry,
-3. So even though ammonium is an acid, ammonia is a base, in terms of redox, these look the same to me. In terms of redox, both of these are fuels, you know. These are, if I have an oxidizer come along, they're going to act, you know, and both of these should burn, although I wouldn't want to burn them, right? And so these look very similar in terms of redox. This one looks totally different. That's what I don't want to hear about all this other stuff because then you're, you know, well, anyway.
It's really about.
So if we're going to use ammonia or ammonium later on, we're in trouble if we have hydrogen peroxide, right? In fact, hydrogen peroxide and ammonium are going to generate a toxic gas, most likely,
Which
which will be some kind of oxide of nitrogen. You know, so most oxides of nitrogen, or you know, it depends on what else is in the mix. You could get nitrogen, oxygen, and chlorine and get something like phosgene gas. Have you ever heard of phosgene gas? Phosgene gas is like a World War I chemical warfare agent. You know, you don't want to mess around and get all kinds of redox products, some of which are going to be toxic. And so we got to worry about that. And this is why, you know, sometimes when you do redox chemistry, it's always a wise thing to do it in the hood, you know, because you vary the conditions a little bit, you're going to vary the products, you know. It's like if you're burning methane, should you do it in the hood? Well, it depends. You know, if you generate carbon monoxide, you better be doing it in the hood. Otherwise, you're going to poison yourself. And, well, how do you know you're going to generate carbon monoxide? Well, you know, you guys know, but you guys need to get a nice deep blue flame. But, you know, if somebody who didn't know that, then you would want them to do it in the hood because they don't know what they're doing, right? Do you know what you're going to generate as far as the gases? Under what conditions? No. Under extreme oxidizing conditions, we're going to generate NO and NO2, but NO and NO2 are toxic. No. You don't want to be breathing that stuff. So, primarily, we need to get rid of the hydrogen peroxide, otherwise we might generate a toxic gas and poison ourselves, basically, all right? Or, you know, it depends on how much ammonia. Obviously, you can always add more ammonia, you know, let it bubble out or whatever. It'll probably stink, and you'll probably say, oh, this stinks too much, I'm going to put it in the hood. But it's probably not going to kill your analysis. Yeah. How do we get rid of excess hydrogen peroxide? It was very easy. You know, you can just heat it up. Heat it up will speed this process up. What's the driving force for this? Formation of gas? What's the driving force for this? The formation of the gas is the driving force? No. This is a redox reaction. Formation of the gas is not the driving force. I suppose we could look at the driving forces, but too much time. So we kill off the hydrogen peroxide. So we heat, what do we say? We heat solution, is this a solution? Heat solution 4. So we'll just say solution 4, heat, and then we should see bubbles, you know, gas or effervescence. And this should be a CCG, clear colorless gas. It should be O2. So it's 5. 6, what are we doing next? We're going to add barium chloride?
Yeah.
No, we don't have any hydrochloric acid yet. And so we're going to take solution 5 plus hydrochloric acid. What happened?
Then you get the yellow chloride. No, wait, sorry, you get the Al3 sauce. And then you add the
Oh, did I make a mistake? Maybe I made a mistake. Did I?
That's much less than that. Because it can say from either something. Add barium chloride.
Did we form dichromate or chromate?
You forward dichromate.
Dichromate.
Dichromate first, and then you add the
All right, then I made a mistake. Unfortunately, I made a mistake.
You make chromate first, and then you make dichromate after you add the hydrochloric acid. And then you add chromate.
All right, then to solution 5, we add HCl, then what happens? You should be able to see it in the flow chart.
Yeah.
What?
It ionizes.
Well, what does it say in the flow chart, in the box, the little box?
Al3 plus CO2%. That's where it selects either the aluminum test or
All right, and so what color is CR207? 2 minus.
That's orange.
Orange. So this
Or orange.
gives us an orange solution. right? When we add the HCl.
Then you add ammonia.
Well, let's stop here. What's the reaction that's going on here? I wrote it yesterday, or 2 days ago on the board. Do you remember what the reaction is? No.
Oh, is that the one with the pH? Where,
Right, it's a pH dependent.
yeah, photodichromate and the water.
Oh yeah.
Yeah, does that ring a bell?
Yes,
That's good, that's good. That means your memory is pretty good. You remember that. If you don't remember it at all, then I think you have normal memory. Most people forget everything. And so this is chromates plus 2H plus yields dichromate plus H2O. Good. That was a reaction. This is just a Lewis acid base reaction. All right, what's next? We're just looking at chromium. We already did aluminum. And so let's forget about the aluminum. What I don't want to see is I don't want to see everything jumbled up. Obviously, the whole bunch of stuff is happening, but let's just focus on chromium and what's happening with chromium in every step of the flow chart. What's the next step? The ammonia? All right, so we take solution 6 and add ammonia.
I think it's the yellow precipitate.
Where did we get the chromate precipitate from?
From the, oh yeah, you add the ammonia to solution 6 and then you get the yellow precipitate. Sorry, I skipped the next step. So this is,
Okay, so we add the ammonia. What's the purpose of the ammonia?
I'm just saying it's there. I think it's to make a basic solution with pH to have that reaction.
Somebody tell me the purpose of the ammonia, if they can see it in there, because it's already basic. Or is it? No, I guess not. Oh, is it to make it?
Oh, it's to separate the chromate ion and the supernatant negative. The aluminum precipitate. That's what it's
So when solution 6 containing chromate comes into contact with ammonia, what happens to the dichromate?
chromate ion is stable neutral and alkaline, which refers to the very dichromate. So you did the reverse of that. So you're converting the dichromate to a single chromate.
So we're just going to go back to yellow? All right. So we go to yellow solution. So that's the reverse here. There are two ways we can show this equation. We can show it by Le Chatelier's. Let's just do it that way. By Le Chatelier's, we have this equilibrium, which is going to depend on the pH. So we have 2 chromates plus 2H plus yields Cr2O7, 2 minus, plus H2O. What's the ammonia? What's ammonia going to do to this equilibrium? Ammonia is going to attack what? The H plus and make 2 ammoniums. And so Le Chatelier's principle says this: as the H plus concentration goes down, the reaction is going to shift left back to chromate. Okay, what's next? 8. All right, so now we're going to take solution 6 or 7. Solution 7 is add barium chloride and get what? All right, a pale yellow precipitate. And so the reaction here is this. This is metathesis reaction. Barium ions plus chromate ions yields barium chromate. call it. We'll do this Le Chatelier shift business here. Okay, what's next?
What's next
Is that the end?
we do iron.
We did iron. So this is the end, and so this is a positive test for what? Is this a positive test for chromate or chromium-3?
Chromium 3.
Yeah, this is a positive test for chromium-3 in our solution. All right, I'm going to stop here, and then why don't you guys go ahead and get started with the lab.